Second problem, we are wanting to accelerate 2 mass units from rest to 3 velocity units, and we're going to then want to increase its altitude, the altitude of the 2 mass units, by 2 distance units. We're given the conditions that to raise 1 mass unit through 1 distance unit requires 10 energy units. If you lower 1 mass unit through 1 distance unit, that provides you with 10 energy units in a way that we'll try to make more explicit. Now we also know that kinetic energy is 1/2 mass times velocity squared, and that the work done by the net force is the net force times the displacement delta S, and that equals the change in kinetic energy. And again, kinetic energy is 1/2 mv squared. When we raise 1 mass unit through 1 distance unit requiring 10 energy units, the potential energy of that mass increases by 10 units. If we lower a mass 1 mass unit, 1 distance unit, the potential energy decreases by 10 energy units. And work or energy can be used to change kinetic energy, to change potential energy, to overcome work by other forces. Now I've changed this work here to work/energy. That might be a little hard to read, but we really want to talk about work and energy kind of interchangeably in a way, well, that we'll see. We're already talking about energy units up here, and energy units can be used to do these things. Work units and energy units are equivalent. Okay. So to accelerate 2 mass units from rest to 3 velocity units, the initial kinetic energy is 0, since kinetic energy is 1/2 mass times velocity squared, and the thing is initially at rest, so it has 0 velocity, so it has 0 kinetic energy. Final kinetic energy is 1/2 of the number of mass units times the square of the number of velocity units. So I wrote that here, 1/2 times 2 mass units times the square of 3 velocity units. Now we're not messing too much with units here, but I'll note that you're going to get mass units multiplied by squared velocity units when you do this. But the main thing is you're going to get 9 energy units. See, we're not going to worry too much about unit calculations here, but we do want to put correct energy units and correct units on the different quantities. Okay, well, so it's going to take us 9 energy units. We're going to need 9 energy units to speed this thing up. Okay, we want to increase the altitude now of 2 mass units by 2 distance units. So what do? Well, if we increase 1 mass unit by 1 distance unit, it's going to take 10 energy units. So if we have a mass unit in each hand, we can raise 2 mass units through 1 distance unit, and each one of them is going to take 10 energy units. So if we raise 2 mass units by 1 distance unit, that's going to take 10 and 10, 20 energy units. Now if we want to raise 2 mass units by 2 distance units, okay, put 1 in each hand, raise them 1 distance unit, that's going to take 20 energy units. Raise them another unit of distance, it's going to take another 20, it's going to take 40 distance units. And pretty quickly we conclude that if you multiply the number of mass units by the number of distance units that you're raising it, you're going to get a number, and if you multiply that by 10, it's going to give you your energy unit. For every mass unit and every distance unit, you get 10 energy units. Okay, so to raise 2 mass units by 2 distance units, which is the condition here, you're going to take 40 energy units. You're going to need 9 energy units to speed it up. Can you do that? Well, no, you've only got 30 units. You can't do it. Okay? You got 49, you need 49, you got 30. You don't have the energy to do this. Okay.